All right, y'all. Today we're going to be talking about logarithms and what they mean. Okay, so first off, let's read through this. So, solving log exponential equations like the ones above are easy when each side of the equation has a common base. But problems like 3 raised to the x minus 1 equals 4 causes problems. So, first off, what are the problems with that? So, this is referring back to what we talked about last week. So, 3 raised to the x minus 1 equals 4. What's the problem? Why can't I solve this directly? So to recall, we were solving problems like so, which give us this. And since the bases are the same, then the exponents match up. The problem here is there's not a direct way of solving this such that 3 and 4 kind of, I can't write 4 as 3 to some power directly. Okay, it doesn't match up nicely. So we have to figure out a way of solving this. Now, keep in mind that you could graph these two equations and they would intersect. We know the 3 to the x minus 4 is some sort of shift. The x minus 1 is a shifting to the right one. So, but this function would look like something like this. Y equals 4 would be a horizontal line. So they would cross. We know for sure they're going to cross. The question is this where. Okay. So with that problem created, we introduced the concept of logarithms. A logarithm, commonly called a log, is simply an inverse of an exponential equation. Okay. So what that means is if I give you something like 2 to the x equals y, log base 2 to the y is x. Okay. And this is what is being expressed here. It's just a different way. It's the inverse of an exponential equation. Students typically hear the word log and go into a cold sweat because they do not understand them. So let's get it straight once and for all. Just as the equations y equals x cubed and x equals the cube root of y are equivalent statements, the exponential y equals b to the x can be written as an alternate form x equals log base by. This is exactly what I just said here. I just used numbers instead of numbers and variables as opposed to just variables. Okay, so the inverse, we say inverse is when you switch x and y, and that's what's going on here, right? So yes, they mean precisely the same thing. So when you are asked to find log base by, set it equal to x, rewrite it as an exponential, b to the x equals y, and solve it like you did above. Okay, so this is the game we're playing with. And again, the real big gist of this is to understand that a log is just a way of writing it as an exponential format. So one easy way that we talk about to do this is we call it the claw. So it's kind of like a dance step. 1, 2, 3. And look what happens here. We have 1, 2, and then 3. And that's how the format is written out. Okay. So how do we go about solving these problems? Well, there's two ways of doing this. One, you can just set it equal to x. And like we said, we can claw it. And we'd get 2 to the x equals 8. And we've learned from the other day that 8 is 2 to the third power. So we can say 2 to the x equals 2 to the third. And because the bases are 2, then the exponents will be equal. We can say x is 3. Another way to approach it is to turn and say, well, hey, what a log is saying is that when 8 is written as 2 to some power, and we know 8 here is really just 2 to the third. The exponent, when 8 is written with a base of 2, the exponent is what the log is equal to. And what I think is so incredible about this is that these two ways of thinking are saying the same thing, right? When I say, how can I write 8 with a base of 2 and say it's 2 to the third? That's what we mean when we write this, what I did in green here, right? 2 to the third equals 2 to the x, and x is 3. It's just a different way of saying that. And that's kind of a cool thing. So what does log base 3 to the 81 mean? And I'll give you a second to think about it. Hopefully you can just say what the answer is. This should be log base 3 to the 4th, because if the bases match up, then it's just the exponent, which is 4. You, of course, can also just say 3 to the x, set this equal to x, and say plot, and say 3 to the x equals 81, and then 81 is 3 to the 4th, so 3 to the 4th equals 3 to the x. Because 3 and 3 match up, x is 4. And there's your answer. Okay? Let's look at the next one. So here we're going to have to remember some of the properties we talked about last week. One of the things we said is that 1 over 25, if you see something as 1 over, that is just 25 to the negative 1. And then 25 we know is 5 squared. And because we're raising it to the negative 1, we have to recall the power rules of exponents. So here we're seeing a lot of our old friends that we've talked about throughout the semester resurface. When you raise something to another power, we multiply. So this is log base 5 to the negative 2. Now, because the bases match up, so do the exponents. I got negative 2. And there's my answer. Okay? So look what we're doing here. All we're doing is rewriting this number, which is the argument of the function, with the base of whatever it is, and then it'll give you the value. Or you can use the x, set it equal to x, and use the claw to set it up so that you can get the bases to match up. Either way, you're getting the answer. Okay, so this one's interesting because 32 is not 4 to the some power. 4 to the first power, write this off to the side, 4 to the first is 4. 4 squared is 16. 4 to the third is 64. So I have a little bit of a problem here, but that's not really a problem. Again, if one method doesn't work, just jump to the other and see what happens. It's kind of like what we do in math. So we'll claw it. We'll get 4 to the x is 32. Now, may seem a little bit of a predicament, but not really, because both 4 and 32 can be broken down. What times what times what is 4, and what times what is 32? Well, 4 is 2 squared raised to the x, and then 32 is 2 to the 5th. Okay, now if you didn't know that, this is where it's important to start to know it. Okay, in other words, as you come across these powers, you should begin to try keep a notebook off to the side and start writing these down. You should know 2 to the 5th is 32. You should know 4 is 2 squared. And if you don't, start writing it down. Over time, you'll start noticing it pop up more frequently. Okay, so this is going to be 2 to the 2x, because remember, when you raise to another power, it's multiplication. Once more, when the bases match up, so do the exponents. So 2 to the x equals 5, and x is 5 over 2. And there's our answer. Moving right along. What do we know about the square root? So notice all we're trying to do over and over and over again is rewrite these as exponents. So the square root of 2 is the same thing as raising it to the 1/2 power. Okay, so I like that. We're going to go ahead and say it's equal to x, and I'm going to go ahead and claw it, which will give me 8 to the x equals to 2 to the 1/2. Once more, if I don't know what what the relationship between the two, 2 is prime, so in other words, 2 is as low as it can get. 8 we can rewrite as 2 cubed, and if you don't know that, well, you should be adding it to a list. You should be adding a list of values that you know, numbers that you see when you see, you're like, hey, I know that's 2 to the third. Hey, I know that's 3 to the 5th, etc., etc. Okay. Once more, we said when you raise to another power, that is the power rule, which means you multiply. And we have it as such. Kind of scary looking, but not really. Just because you have a fraction is not a big deal. We're going to get 3x equals 1/2. I don't like that 3 there. When I have fractions, instead of dividing through by 3, I always like to say multiply through by 1/3. X is 1/6. And there's my answer. Okay. All right. Moving right along. Okay. More of the same. Index here. So notice, I want to make one note here. This is a lot of times people don't realize. There technically is an index value of 2 here. And the index tells you what the denominator is of the exponent. Okay. So here the index is 3. So this means that this is the same thing as saying log base 25, 5 to the 1/3. Once more, not sure, set it equal to x. Claw, 25 to the x equals 5 to the 1/3. 25 is 5 squared. When you raise to another power, that's multiplication, so we're going to multiply that. That's going to be 5 to the 2x equals 5 to the 1/3. And then we're going to say 2x equals 1/3. And I'm going to do the same thing that I did before. So notice here, like I said, whenever I get 3x equals 1/2, actually, it's just the numbers kind of reversed. When I see this, I like to multiply by the reciprocal as opposed to dividing. This means the same thing, it's just a little easier. I'm going to multiply by 1/2, multiply by 1/2, will let me, and x is going to be 1/6. And something else to keep in mind, you can always take, if you have any doubts, once you set it up like this, you can always plug it in and test them, see if 25 to the 1/6 equals 5 to the 1/3. Always do that on the calculator. Okay, so this one here has a combination of 2 effects. One, this is written in the denominator, so we know that we can rewrite 1 over square root 6 as square root 6 raised to the -1, right? And that's an important property. We also know the square root is the same thing as raising it to the 1/2. Okay. And we also know, just for funsies, we also know that when you raise something to another power, we can make it we could multiply them. So we just multiplied these two together, got -1/2. Okay. We're going to set it equal to x. We're going to claw it. We're going to get 36 to the x equals 6 to the -1/2. 36 is 6 squared, so 6 squared raised to the x equals 6 to the -1/2. So this is 6 to the 2x equals 6 to the -1/2. And again, if the bases are the same, then the exponents are the same. So 2x equals -1/2, and multiply by 1 over 2. And x is equal to -1/4. And there you have it. So, moving right along. This is a great one. Short and sweet. 1, we know anything raised to the 0 power is 1, so we'll just say this is 9 to the 0. And now, because these two match, it's just 0. So actually, a log of anything, it doesn't matter what the base is, it doesn't matter what this little number is. If this is 1, it's 0 automatically. Now this one's very interesting. So we're going to say it's equal to x. We're going to claw it. We get an interesting situation because 9 to the x equals 0. Now one thing you could do is you could graph this, and if you did choose to graph it, you would get a graph that looks like this. Because we've talked about asymptotes, I can use this terminology here, and so it is asymptotic with 0. Okay, so this is just to be clear, this is y equals 9 to the x. That's what I'm graphing here. And what do we notice? Well, we notice that it never hits 0. So because it never hits 0, it's impossible for 9 to the x to equal 0. So this actually does not exist or the empty set. Another way of thinking about it is just to plug in numbers. So plug in -3, that gives you a fraction. Plug in 0, that gives you 1. Plug in 2, that's giving you 81. It's giving you a pretty big number. So just by playing with numbers, you know that it's not going to work as well. Remember, you can always type these things into Desmos, and it'll give you the desired result. So there we have it. All right. So now we have a negative. So we'll do the same thing. We're going to set it equal to x. We'll claw it. We get 3 to the x equals -9. So recall here that this thing never gets to 0. So it's definitely never going to get to a negative. So by the same argument, we know it does not exist. Or by the same argument, we plugged in a negative, we got a fraction. We plug in 0, we get 1. We plug in 1, 2, 3. We're getting really big numbers as x keeps getting bigger and bigger. This thing never gets to a negative value, so it does not exist. All right, this one's interesting. So what a good strategy is in general is when you see a situation like this is to just always begin by trying to get the function by itself. I don't care if this is x cubed, x squared, log, sine functions, cosine functions, all these things that maybe you've never seen before. The nice idea, generally speaking, is to get the function by itself. And then, even though it may look a little ugly, that's okay. We're just going to claw it. So we get 4 raised to the x minus 5, x over 5 rather, is equal to 8. And we've seen this situation before, 4 and 8. You can't rewrite this. You can't break 8 down to 4 directly, but you can break both 4 and 8 down to 2. So that is exactly what we're going to do. 4 is 2 squared, raised to the x over 5. 8 is 2 cubed. When you raise something to another power, we said that that is multiplication, so this is now 2 raised to the 2x over 5 equals 2 cubed. And once more, because the bases match up, so do the exponents. So this is 2x over 5 equals 3. We're going to multiply both sides by 5. These colors are not too distinct. Apologize about that. So this is 2x equals 15. Finishing this off, we're going to divide through by 2. Nice little contrast. And x is 15 over 2. Not a perfect integer, but the answer nevertheless. Okay, so get the value by itself, value being inside the function by itself, and then use the claw. All right, same deal. So this, we'll say this is equal to x. Okay, just to make life a little easier, we'll go ahead and take the square root of both sides. So log base 9 to the 1/3 equals, now remember square root is to the 1/2 power. And from here, we can claw it. So we get 9 to the x raised to the 1/2 equals 1/3. All right. Now, you may be getting a little scared here, but don't panic. First things first, get rid of the fraction. So 3 and 1/3 is 3 to the -1. 9 is raised to the x raised to the 1/2. Next up, 9 is 3 squared. And I'm just going to go ahead and say it's 3 raised to the 2x to the 1/2, and this is equal to 3 to the -1. So look, we had to do a little more math, but it's just about getting the bases to match up, because once the bases match up, then the exponents match up. And I can just say 2x to the 1/2 equals -1. The goal here is to get x by itself, so we'll divide through. And this is going to become -1/2. Now we will square it. And x is equal to 1/4. And there's our answer. Okay, so a little more work? Yes. Do you need to know your algebra? Yes. Is it Is this impossible to do? Absolutely not. Okay, so we're going to move on now to the next part of the topic, which is it impossible to take logs of zero or negative numbers. We saw that, right? We saw up here a log of a negative does not exist, and we saw here a log of zero does not exist. And that's because these functions, as they get closer and closer to, this function gets closer and closer to zero, but it never crosses. So it can never be zero or below, right? Or if you plug in numbers, you'll realize it doesn't work. Very important to know. Okay, what's that next? So log base 3 of 0 does not exist as there is no number x such that 3x equals 0. This was the argument. The same thing is true if the argument is negative 3. There's no number x such that 3 to the x equals negative 3. We can only take logs with positive bases not equal to 1. If the base is not specified, and this is the other very important point, it is assumed to be 10. So log base 10 to the x is the same thing as log to the x. So we usually like to use 10. This actually comes from the fact that we have 10 fingers. And this is called the common log. So if you see something like log 100, don't freak out. You know that this just means log base 10 of 100. By the way, 100, and this is another reason why we like it, is just 10 squared. How do I know it's raised to the second power? Because the number of zeros tell me that, right? So if I have 2 zeros, it's raised to the second power. When these bases match up, it's just the exponent. So 2. So in other words, if I see just the log, I just count the number of zeros, and that's my answer. Okay, so what about log 1? Well, again, we can say that log 1 is log base 10. 10, what do we know about 1? It's 10 to the 0, so this is equal to 0. Or you can simply say, hey, remember when we were talking about this at the very beginning? Let's see here. Right here? I said anything that's raised, the argument is 1. What's inside the log is called the argument. So this 1 value is the argument. If that happens anytime you see 1, it's just 0. So that's kind of cool. We're seeing the rehashing of all the stuff we talked about before. Oh, look, 1 over 10. What do we know about fractions? If I want to rewrite it without a fraction, I can just raise it to the negative 1. What do we know now? Oh, look at that. These two values match up. It's just the exponent, negative 1. Nice. Okay, what about this? Set it equal to x. Get rid of the 2. Right, so square root, or I like to say raised to the 1/2. I think it's a little easier. By the way, that reason why we take the square root is because the power rule says if you raise it to the 1/2, 2 times 1/2 is just 1, so eliminates it. We also know that a log, if there's just a log, it means base is 10. We also know that if I don't want to have fractions, I just raise it to the negative 1. So now I'm here. What else do I know? Well, I also know that I have 3 zeros. So this means this is the same thing as log base 10. 10 to the 3rd raised to the negative 1, which is also, we know, is also the same thing as saying log base 10, 10. The rule is that when these match up, you multiply. Negative 3 equals x to the 1/2 power. Then we also know that when this and this match up, it's just negative 3. So negative 3 equals x to the 1/2. And then now I don't like the 1/2, so I square it. Because the power rule says when you multiply, notice we're doing this process here over again. This gives me negative 3 in parentheses squared, which is x. Now this is important. This will give me 9. If you type in the calculator negative 3 squared, it will give you negative 9 because the calculator follows PEMDAS exactly. That's not what we're saying. We're saying the quantity. So this is incorrect. The answer would be x is 9. So A lot of work to get there, but not too bad of a problem. Okay, so what about this one? Well, all we got to do here, now I can say it's equal to x, but I'm going to keep it simple here. We can say this is base 10. 10, we know the square root means the index is 2, so this is raised to the 1/2. These two match up, so this is just 1/2. The only new novelty, the only thing that's different in this problem is it has a 5 here, so we have a 5 in the front, and so at the end we just multiply. We get 5 over 2. Okay, more of the same here. So they're trying to trick you by putting a negative in the front to say, oh, you can't do anything, but that's not part of the log. The log is being raised to the 1/3 because the index is 3. Once more, because these two values match up, this is just 1/3. The -3 is still in front. That's going to give me -1. This is the one that I really like because there's just a base 10, so this is just 4. I hope that this is starting to click. Oh, look, there's a base 10 here, so this is just square root 5. All right, next bit. Okay, in mathematics, we have a very special number, and it's called Euler's number. Euler's number discovered this, Leonard Euler, discovered this number and is known as E. The value of E is 2.7182, blah, blah, blah. E is a transcendental number which, like pi and square root 2, continues on forever and ever without a pattern. Note, the 1828 in E, although appearing twice consecutively near the start, does not appear for a very long time. It is completely coincidental that it appears twice. The number E is an important number. So you start talking about the 5 most important numbers, which I believe are pi, let's see here, pi, E, 0, 1, and I. Okay, those are like the 5 most popular values. And there's a famous equation called the beautiful equation, which I'd tell you to look up, that has these values. That it forms the basis of what are called the natural logs, okay, of Naperian logs, based off of John Napier. By the way, John Napier is French, and that's why it's the symbol, which is ln here, for natural log, is reversed because in French we flip the order of the adjective. So basically, E, and we're not going to get into the specifics of what is so significant about E, but E is a very powerful number in mathematics. It's used a lot in terms of exponential growth, but it also appears in a lot of other places as well. But that's usually where you see it in high school. Anyways, so that's why they use it. But the same pattern emerges. So this is what's important to realize, is that when you see ln, this is just log base E. So once more, if these match up, I want to switch up, then the answer is the exponent. So here, 2 bits, we know that ln, and this is what I recommend doing. If you see ln and you're not sure what to do, just call it log base E. Again, because they match up, -1's the answer. Square root, not a big deal. We know ln is log base E. We know the square root is 1/2. The bases match up. It's equal to 1/2. ln 1, not a big deal. It's log base E to the 1. What have we said repeatedly? This is the same thing as log base E, E to the 0, right? Anything to the 0 power, almost anything to the 0 power is 1. This matches up, so it's 0. Actually, anything log of 1 is 0. What about this one? We'll clean up the front part. I'm now just going to say 2. It should be noticeable that this is just the exponent, so it's just 9 times 2, which is 18. And this is what should be happening as you practice. What about this? This is just 1/3 ln e to the negative 3. We've done so many of these, it should be starting to become rapid fire. This is just negative 3 times 1/3, which is negative 1. What about here? Okay. Well, here this does not exist. Why? Because we said logs can never be negative. This value here cannot be negative. Okay. And here's a very special case. Okay. So here's where we're kind of I'm going to kind of allude to some of the things that we'll do in the future. When you first see this, you follow the same strategy of setting equal to x. Now the problem is because we have an e here. This is where natural log is so useful. If I put a natural log on both sides, I have natural log e to the natural log 5 equals natural log of x. And the cool thing here is, what have we been saying? Well, we've been saying that if you have ln and e matching up, right, they go away. So you're left with the exponent. So this is natural log 5 equals natural log x. So what does that mean? Well, that just means, let's go back to our traditional colors. That means 5 is x. Right? If this is natural log and this is natural log, then 5 and x have to match up, and x is 5. In other words, what we're saying is that if you see e ln 5, this is not exactly what's going on. Those go away, and the answer is just 5. Okay, well, that was a lot, but I felt like we needed to practice a lot of problems, get a lot of drill and kill so that we can make sure that we do well on the exams in the future. So hopefully this wasn't too bad and y'all are doing okay with this. And if not, reach out to me and I'll see what I can do to help you out. Otherwise, I will find you in the next math video. Thanks, guys. Keep working.